Okay, we did everything with relation to refraction at a spherical surface, Lensmaker's formula, thin lens formula. I'll come back to that, but I just wanted to go back to total internal reflection. And before going to total internal reflection, wanted to cover one thing with you. Let's revisit Snell's law once again. Okay, if you see Snell's law, then always have the diagram clarity in you when you are seeing Snell's law. This is angle of incidence and this is angle of refraction. Let's say this is medium 1 and this is medium 2. Okay. Snell's law says that sine of I upon sine of R is equal to, okay, refractive index, which we are representing with eta, and we say that refractive index of it will be measuring 2 with respect to 1, means from where the light is incident, and in your book you are writing this as eta to 1. Is this fine? Okay, we bring the same analogy now for total internal reflection, because I saw some numericals are there, but this formula is now not mentioned in your book. But still, total internal reflection. Now let's look at total internal reflection. Okay, in total internal reflection, this is a medium, and this medium is usually children has to be denser, like glass, diamond or something, right? And let's call this medium as, say, 2, and let's call this medium as 1. Okay, let's call this medium as 1, and 1 can also be air, 1 is air, let's say, right? Your ray of light will be actually coming from here, and there's the normal, and at total internal reflection, if this is your critical angle, then your angle of refraction is equal to 90 degree. Is this thing fine with you, right? So let me formulate Snell's law again from here. So I would write sine of critical angle upon sine of R, which is equal to sine of critical angle upon sine 90, right? Which is equal to sine of critical angle upon sine 90 is 1. So here, okay, fine. And how do I write it? I would write it as eta. We always take from where light is coming. The light is now coming from, the light is now getting out. It is inserting inside 1 with respect to 2. Have you understood this part or not? With respect to 2, because the light is actually coming from 2 and it is getting inserted inside 1. How do I write this, children? I can write this as eta 1 with respect to, sorry, eta of the air with respect to the medium 2, right? Just see this part, eta air with respect to 2. Can I write, if 2 is, say, some medium m, if 2 is some medium m, then how can I write this? I can write this as sine of IC is equal to eta air with respect to some medium m. Agreed? I can then write it as 1 upon eta m with respect to air, which is nothing but 1 upon eta m, just because once. So from here I can write that eta m of a medium, of a very denser medium, which is allowing total, or which is obeying total internal reflection, the refractive index of that medium is always 1 upon the sine of critical angle. Let's make a note of this one. Did you understand this? Arjun, clear? Okay, just make a note of this and then we go further. Why I have written in this manner? So that even if you forget, it becomes easy for you to deduce and find it out. Once done, just let me know, then we will proceed. Shall we? Okay. So just a recap of the formulas that we saw in our last class. The first one was refraction at a spherical surface. Refraction at a spherical surface. And we said that it's like eta 2 minus eta 1 upon r is equal to eta 2 upon v minus eta 1 upon u. Care to be taken, eta 1 is from where light is coming, eta 2 where light is entering. Always remember that. Eta, and that is standard for this formula. Eta 1 is from where light comes, and eta 2 is where light enters into. And if you remember, the diagram for this was like all these sides were eta 2 and this side was eta 1. Remember that, right? Fine. Okay. Then we went to our next formula, which was our lens maker's formula. In lens maker's formula, we said that, we said 1 upon f is equal to eta 21 minus 1, okay, 1 upon r1 minus 1 upon r2. Where if you want to find out what is eta 21, then r basic says eta 2 with respect to 1, right? And if you want to do it like this, eta 2 with respect to 1, and you want to make it, so how do you write it? You can put eta 2 with respect to air into eta 1 air. So this is nothing but eta 2, and this can be written as 1 upon eta 1 air. So this becomes eta 2 into 1 upon eta 1, which is eta 2 by eta. So 2 1 can be written as eta 2 upon eta 1. Get your basics clear, so that you don't goof up on anything, right? And then the thin lens formula. The thin lens formula was 1 upon f is equal to 1 upon v minus 1 upon u. This is thin lens formula. Actually, children, when you derive this formula, you actually get this one only on the left hand side, 1 upon v minus 1 upon u. And we say if the object distance is at infinity, then v will be formed at focus, right? So 1 upon, did you understand how you get this one? This is 1 upon v minus 1 upon u. If u is infinity, v is focus, f. So the same thing comes up. Clear this much? So we proceed further. Can I? Okay. Then we also need to know the formula for magnification. The formula for magnification is grade 10. Magnification is given by height of the object over height of the image, also given as v upon u. Whereas in the case of mirrors, you will have a negative which will precede the v. In the case of mirrors, we will have a negative v and a HO over HI. Okay. Based on this, we will just see some image formation. I mean, this is repeat of grade 10. Image formation. Okay. Formation rules. And we will see for both type of lenses, the convex lens as well as the concave lens. Now There's a concept called plano-convex. What's a plano-convex lens? A plano-convex lens is straight on one side, either this or this. This is a plano-convex lens. What we study is called a double convex lens. So a double convex lens would be and similarly you can also have double concave. Double concave is a combination of two plano concaves. So plano here, double concave lens. Fine. So let's see it with respect to a double convex lens. This is my double convex lens. A double convex lens will have two focus. One is called the first focal point. So we will have an F, which is called the primary or the first focal point. And the first focal point is always taken on the side where the incident light is coming from. And obviously, you know, incident rays are always traveling from left hand side to right hand side. That's the what do you call the convention that we take. And this is my F dash, known as my second focal point. And that would be true even for a concave lens also. A little bit of grade 10, okay, children, little bit of grade 10. So if you see in grade 10, how do you define the focus of a convex lens? It is the point where rays converge upon. All right. So your this particular distance, this distance would constitute what is known as your focal length F, and that's why this is positive for a convex lens. A convex lens converges, so the focal length is always positive because you're measuring on this side. Whereas if I look at this lens, okay, if I look at this lens, then the rays will appear, it's a diverging lens, the rays diverge out. So in this case, if I measure this distance, this will give me my focal length, and my F would be negative in this case, right? Further things that we should know, that this would be a real focus because actual intersection of rays takes place here, and this will be a virtual focus. Get your understanding and then start drawing. Should you find any problem, you can always look at the board. You can always. Okay, like you had a pole of a mirror. In these cases, we call this point as the optical center. This is O. O is my optical center. O is optical center. Can I slowly change the slide? Arjun, fine? Okay. So when we form images in this particular both type of lenses, just 1 minute, okay, when we form images, let us see what are the criterias that we actually use. Okay, so my principal axis, as usual, I'm trying to do it for both. Fine. So you need minimum 2 rays to actually intersect after refraction to get the image formation, or if they don't intersect, for their extrapolation. So the rule is, if you are parallel to the principal axis, if you are a ray which is parallel to the principal axis, obviously I should have marked my focus. So this is yeah. So if you're parallel to the principal axis, if the ray is parallel to the principal axis, the ray after refraction will always pass through the focus. Fine. If the ray is actually, if the ray is coming from the focus, it will always become parallel to the principal axis, right? And if there is a ray which is through the, sorry, if there is a ray which is through the optical center, that ray will go undeflected. To go undeflected. Fine. A ray parallel to the principal axis passes through the focus. A ray through the optical center goes undeflected. And if you have a ray which is through the focus, now story becomes a little bit different in case of what you call concave. In concave, though I'm doing it in a wrong manner just to make the diagram look correct. So if the ray of light is parallel to the principal axis, it appears to diverge out from the focus. It appears to diverge out from the focus. Fine, children. And And if you had a ray which is actually targeted to the focus, so somewhat like this, okay, this ray will actually become parallel to the principal axis, after refraction. The dotted actually shows where it was targeted at. And a ray through the optical center goes undeflected, holds for here also. Means you can very well take a ray from here and go undeflected. Fine, children. Okay. Our next topic would be power of a lens. Again, something which you have read in grade 10. Power of a lens. Power of a lens, we say it is the measure of the extent of convergence or divergence of a lens. It is the extent of convergence or divergence of a lens. So let's say there is what you call a principal axis, and I have my lens out here. Okay. I have my lens out here. Now see, children, although in grade 10 you have written power, read power is 1 upon focal length. How does this come? Now this much is the angle of deflection. This, you know this symbol, this is small delta. This is small delta. So as per alternate interior angle, this will also be small delta, right? And let us take this height as h. And then what is this height? This height is f. So we write that the power of a lens P is given as the tan of the angle of deviation, or tan of the angle of deviation, that is the angle by which a ray is deflected or is deflected away from its path, right? Now if you want to take tan of delta, what will it be? It will be h upon f, right? And here we say h is equal to 1. So the definition is like this. See, what is power of a lens? Power of a lens, listen to me, power of a lens is tan of the angle of deviation of a ray which is at a unit distance from the principal axis. Means unit distance means at a distance 1. Power of a lens is tan of the angle of deviation of a ray which is at a unit distance from the principal axis. So h equal to 1, and this 1 is coming because you have taken unit distance. है ना? In that case, we get power measured as 1 upon F. And the SI unit of power is diopter. Diopter. Written as D, and F is always expressed in meters, children. F is always expressed in meters. Now tell me one thing. If a lens has got a shorter focal length, its power will be more. Look at this ratio. If the denominator is less, obviously the quotient will increase. So if the, assume you follow this one. So if the focal length is less, the convergence is more. So lenses, so again a 1 mark question as assertion or something might come up. If the lenses have got a shorter focal length, their convergence is much more. That means they will bend the what you call ray much more. And if it was a concave lens, then it would deviate the ray much more, right? So power is always inversely related to the focal length. Shorter focal lengths have got more convergence, and greater focal lengths have got less convergence. Another thing to be seen here is, if you, since I had taken what, children, I had taken a convex lens. So in a convex lens, my F is always positive, so my power will be always positive. So all people who are wearing positive power, like me, at my age, I'll wear positive power, let's say plus 2.5, 2.75 or 2.25 plus power means I'm wearing convex lens. So if you take out my specs and you put it on any word, the words will come bigger in size because this is like a magnifying glass. Whereas Zoe's power will be negative. That means, why is her power negative? Because Zoe is wearing what is known as a concave lens. In case of a concave lens, the F will always be negative because the F will be on this side. Look, the F will be on this side. So her power will always be negative. And at this age, you all will have negative power because you all are all victims of myopia. Rare case at your age, somebody will wear plus power. 1 in hundreds, you can say, which is a hypermetropia. But when you age up and get it more than 35, 36 to 40, then you will have something called presbyopia that you can't escape, even if you are the most beautiful person in the world. So you will have a plus power. So at that time, she will be having both plus and minus. The minus she is inheriting, and the plus will come because of the biological age factor. So she will be wearing a double power. Like I slowly got minus power. So now I'm wearing a progressive lens. My top part is negative, the bottom part is positive because I read from the bottom, I look at you from the top side. Or else you can wear a bifocal lens, the ones which you see semicircular. The progressive ones are much more costly and they're much more easy to what you call adjust it to the human being. Is this one clear? So up till power we are fine. Shall we go to the next one? The next topic is combinations of thin lenses in contact. So we're going to study combination of thin lenses. Thin lenses in contact. Thin lenses, very thin two lenses we will have in contact. So let's see. Okay. So this is my principal axis. Sorry. This is my principal axis, and I'll have very thin lenses which will be in contact with each other. Let's say it's like this. Two thin lenses in contact with each other. All right. So let's pick up an object. Our object is somewhere here. So this is the ray which is coming out from the object. Fine. So this ray, yes, and then but in actual, the image will be formed this way. He will bend it. Okay, tell me if you have not understood. This is the object. The ray is refracted by the first lens and should have actually, after refraction from the first lens, should have gone like this, encounters the second lens, which is again conversing it further. So this is my image 1 and this is my image 2, the final image. The final image is formed here. Can you mark the? Not necessary in this drawing. If you want, I can do it, but it is not necessary because we are not showing any parallel. We have kept the object beyond the focus. Okay. Now see the beauty. This I1 has been taken to actually illustrate the whole picture. It's two lenses in contact. So what happens is the first lens will create a real image. I1 is a real image, and the real image will act as an object for the second one. And at that time, the object is kept on this side. That we have to keep in mind. Shall we? So for the first lens, okay. So for image formed by, so let's name the lenses. Let this be A and let this be B. So we say for image formed by A. So what is the formula we have? And let's say the focal length of the two lenses is, has a lens focal length of f1 and this has a focal length of f2, right? So I write 1 upon, now 1 upon, it will be v1, 1 upon v1. Children, what is v1? V1 would be my distance from here to here. And the second distance is here. What you have to understand is this part is negligible. Did you understand? Negligible. The difference between the two lenses is very, very less. It is negligible. So shall we write 1 upon v1 minus 1 upon u is equal to 1 upon f1. Any doubt in this? Right? So let's take for image formed by B. Okay, let this be equation 1. Image formed by B. Okay. When you're taking the image formed by B, children, your image distance now is how much? Your image distance, this is V1, this is V, this is U. Correct? So image distance is 1 upon V, right? And then I have got my object distance is how much? Minus 1 upon V1. This is my object distance. Fine. When we do the mathematics, we will be taking the, what you call, we will be taking the convention as per the, we'll take the, we'll massage the data as per the sign. This will be equal to 1 upon F1. This will be 1 upon F2. Fine. Equation 2. If I add up both the equations, that is, I do a 1 plus 2, then in that case, what happens, children? This one will nullify this one. Agreed? And then you get a 1 upon V minus a 1 upon U equals to a 1 upon F1 plus 1 upon F2. Now look at this particular expression. This expression now tells you that the combination of two convex lenses, now mind you, I have taken two convex lenses. Combination of two convex lenses actually creates a system of one convex lens. Same formula. Creates a system of one convex lens, right? And I can finally write it as 1 upon V minus 1 upon U is equal to 1 upon F, where now 1 upon F, where we say this 1 upon F is equal to 1 upon F1 plus 1 upon f2 plus 1 upon some f3s dot 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 as they could have been, right? But care to be taken that if you would have done a combination of a concave and a convex, then the effective focal length will be a 1 upon f1. If the second one is a concave, minus 1 upon f2. Third one is also a concave, minus 1 upon f3. Fourth is a convex, plus 1 upon f1. Have you understood? So it's an algebraic addition. So this will be an algebraic addition. We deduce the formula taking two convex lenses. But if that it was a concave lens, so finally everything depends upon the initial object distance and the final, what you call, image distance will obey the same lens maker's formula. So based on this, I can also say that the combined power would be an addition of the power of all the lenses. Yes or no, children? Right? The combined power will be this. But one care to be taken, if there is overall, the magnification would be the product of magnifications of each cases. These three things you need to take care. Focal lengths, 1 upon f add up, power adds up. So I've got how much? A 2.25 plus power. If you bring another plus 1, so my power becomes 3.25 straight away. And if I take her specs, say suppose she is minus 1, then my 2.25 now becomes 0.5, 1.5, 1.25, because the concave will correct out the additional convergence that I'm having. That's why they say if your eyes are too bulged, suppose your eyeballs are too bulged. If you have two bulging eyeballs, means what happens? You are converging the image. That is what is the problem in myopia, when you suffer. So what do we give you? We give you lenses which will nullify that extra bulging. So we give you concave lenses. Whereas in my case, it should bulge. But since I have aged, my ciliary muscles are now weak and they are not able to bulge the lens. So I am putting an extra convex lens to converge the rays. Okay? Yeah, we will do problems. We will actually do problems. Don't worry. This is just for your generic understanding. Remember, the formula is always an algebraic addition. You convex concave also you will do this. We will take up a formula problem from here, which will be exactly a combination of this. So as you have said, let's take one problem and try to solve that. Shall we? So it's from your textbook itself. So let me draw the diagram, because it's a diagram. The diagram is given already. So let me draw it first. We have three lenses. The first one is a convex. The first one is a convex lens, right? The second one is a plano-concave. The second one, and my third one is again a convex lens. Okay. So I have 5, 10. 5 centimeter, 10 centimeter, and this is 30 centimeter. And the object is out here. This is my object, which is O. The first lens has plus 10. Okay. The second one has minus 10. And the third one has plus 30. Now see some beautiful things out here before we go with the problem. Just see. The first one is a concave, which is plus 10, and this is plus 30. More is the focal length, more is the curvature, less will be the convergence. Less is the focal length, less will be the curvature, more will be the convergence. Means you're more rounded now. Okay, understood? So let's say it is said, find the position of the image formed by the lens combination. You need to find the position of image formed by the lens combination. Find the position of the lens image formed by the lens combination. So how we will proceed? We will first see the image formed by the first lens. Okay. Whatever image will be formed by the first lens will become object for the second lens. Second lens will form another image, will be object for the third lens, and then you get the final image. So let's start. Image formed by first lens. And when you say first lens, you can mention the f is plus 10 centimeter is the focal length. So let's start. The first lens image, 1 by v1 minus 1 upon how much? U is equal to 1 upon f1. Agreed? So 1 by v1 minus 1 upon minus 30 now, obviously because your object is at minus 30, is equal to 1 upon how much? 10. How much will v1 come? v1 should come something called 15 centimeters. Just check. Right? Okay, fine. Shall we go ahead now? So next we will find out what? Image formed by second lens. And second lens has an f equal to how much, beta? Negative 10 centimeters. So we write 1 upon v2 minus 1 upon, now this will be minus 1 upon v1 is equal to 1 upon f2. All right? Okay. So we write 1 upon v2 minus, now what is v1? v1 is 15 is equal to 1 upon, yeah, I forgot that. Absolutely. Okay. Now very good, Zoe. Now this is 15. Look, this is 15. Your image has formed 15 centimeters on this side. but 15 is measured from here. But for this particular what do you call lens, the object, which is the image of this lens, will be at 15 minus 10 distance. Is this clear now? Right. So we can write here 1 upon v1 will be how much? 15 minus 5. I hope you understood what is the 5. The 5 is inter lens spacing, and this should be equal to how much? 1 upon negative 10. So you will get 1 upon v2 to be equal to negative 1 by 10. This is this, and this becomes 10 negative. This becomes positive 1 by 10, which is equal to 0. That means v2 takes a value of infinity. V2 takes a value of infinity. Now look, this is a concave mirror. This is, sorry, concave lens. Where did you place the object? You place the object on this side, and the image is formed at infinity, right? Now let's go for image formation by third lens. Now the third lens has a plus 30 centimeter. So this will be the final image. So it will be 1 upon v minus 1 upon u. 1 upon u is 1 upon infinity. Agreed? So rather than that, I should write first step as 1 upon v2 is equal to 1 upon f3, or 1 upon v minus 1 upon infinity is equal to 1 upon 30, or 1 upon v, 1 upon infinity is 0, is equal to 1 upon 30. So you are getting v is equal to 30 centimeter positive. So the image is formed 30 centimeter. Now how will you decipher this answer? Where is the image formed? Image is formed 30 centimeter. Now how will you decipher this answer? No, not positive. 30 centimeter is measured from where? From the third lens. Remember that. Whichever lens you are calculating for, the measurement is always from that lens. So 30 centimeters. So V is 30 centimeters. So we say image is formed 30 centimeters from lens 3. And if they would have said how much from lens 1, then this 10 centimeter and 5 centimeter. Another question comes up, children. Why, sir, did you not massage this 10 centimeter? You massage this 5 centimeter out here. Why didn't you do it? From infinity, even if you take away 10 centimeters, it doesn't matter. So we did not use that. Fine. Okay. With this portion, we actually move to Prism, but we'll move to Prism tomorrow. A couple of more sample problems are there. We'll just take up one more sample problem. Okay. Are we fine on this? Can I go ahead? Okay, let's take one more sample problem and see its workout. So, we had, and I'll tell you to make some minor adjustments in the formula which will actually help you to solve any problem. Refraction from a spherical surface. We have three formulas. So, refraction from a spherical surface. Now, this formula was that we used to say eta 2 minus eta 1 upon r, which is to be a spherical surface, is equal to eta 2 upon the image distance minus eta 1 upon the object distance. I have nothing to say on this formula. Only here I would like to stress once again what I had said yesterday, that eta 2 is always the medium in which light is entering. Eta 1 is the medium from where light is coming. Okay, here eta 2, and then we'll solve the problem again. Eta 2 is medium in which, hang on, this is going to hang up. Wait. Hey Zoe, what happened? Have you woke up or not?
So I started drawing my computer.
Oh, in which light is entering. We will solve this yesterday's problem so that there is no ambiguity now. And eta 1 is medium from where light is coming. So if you see the derivation, if you see this derivation for a single refracting surface, then in that case, I can also write this as, this can be the eta of the lens, this is the eta of air. Agreed or not? These will be case based. You have to do it like this. This is eta of the lens divided by V minus this is eta of the air U. This is when light is coming from air and is entering into a lens. Okay. And eta air is always equal to 1. Is this understood? Eta air. So you have to read the problem and then apply the condition. Eta air is always equal to 1. Now, after that, the class previous to yesterday's, we learned about what was the lens maker's formula. Now here will be all the challenges. Lens maker's formula. Now the lens maker's formula gives me a formula which is 1 upon f is equal to, we have read it like this, eta 2 1 minus 1, and we write here 1 upon r1 minus 1 upon r2. Now take your time, we will debate another say 10-15 minutes on this particular formula itself. I would like to change my screen, right? Now fine. Okay, this formula you have to be very, very careful. I'm changing my screen. So our formula is 1 upon f is equal to eta 2 1 minus 1 upon r1 minus 1 upon r2. Now let's first check each one of them. Okay, this is the standard formula where eta 2 1 stands for refractive index of medium 2 with respect to medium 1. Medium 2 with respect to medium 1, right? That means light comes from this medium. Light comes from this medium, and here I would write light enters this medium. Is this okay so far? Okay. Now, eta 2 upon eta 1 can also be written as eta 2 with respect to 1 is eta 2 upon eta 1. This also I had shown yesterday, right? Now, all our problems that we usually get, we will find that the lens is kept in air. The lens is kept in air. So mind the language. Lens is kept in air. So how do you expect? This is a lens. I'm just drawing one surface of the lens. The lens is kept in air. So light will be entering from air and will be getting inside the lens. So let's massage that formula now. So it will be, if I say this is eta of the lens and this is eta of air. Perfect. My formula then becomes 1 upon f is equal to eta lens by eta air. Lens to air. Okay, so let's say lens to air is eta lens upon eta air, right? Minus 1 into 1 upon r1 minus 1 upon r2. Now I'm just swinging this side. Now the light can enter from air. The light can enter from any other medium also. So why I'm being so stepmotherly with air only? Let me replace this air with any medium. Any medium. If light rather than air is coming from any medium, then I can replace this with eta m of that medium. It can be water or whatever it is. So my formula becomes 1 upon f is equal to eta lens divided by eta medium minus 1 by r1 minus 1 by r2. So if you actually see this part of the formula, we have addressed how to attend for case-based problem. If the lens is kept, if the lens is kept in water, then the refractive index of the lens to the refractive index of water from where the light is entering. Okay, if it is kept in air, then it is in air. Now we will massage this part. Is this part understood? This part is okay. Okay, then we will go for what you call yesterday's problem once again. Now we will see this part, R1 and R2. Now there are many approaches to see R1 and R2. R1 is the radius of surface where incident light strikes first. Where incident light strikes first. So let me make one lens, okay? This is called a double convex lens. What is this? A double convex lens. A double convex lens is made from two spherical surfaces. Can I include this side as yellow? Then I can make this side as yellow, right? And this has got a center of curvature which is called C1. And then there will be another surface which will be, I'll make it with say purple. So this is the other surface. Can I make this purple now? Yes. So this is C2. You tell me, where will the light strike first? The light will first strike the surface, yellow surface first. This is the lens. The light is going to strike the yellow surface. This is out of your mind. Huh? This is just drawn. All of you, are you clear on this? The light is going to strike the yellow surface first. So which surface the light strikes first? Yellow surface. So my R1, C1 corresponds to R1. R1 would be the radius for the yellow surface. R2 would be the radius for the purple surface. Okay. Now, there is another way to understand it. Now, this R1 and R2 are very strange measurements. They will be always measured from what I call as the optical center. Oh, sorry. Now, this is my optical center. My R1 and R2 will be always measured from the optical center. Now, you would say, sir, the radius is from here to the yellow surface. But if you measure from optical center, what happens to this part? This is very thin. So this part is negligible. So if I want to measure the yellow surface radius, I would be measuring in what manner? Instead, coming from the circumference, I will come from the optical center. Which side did I go? Positive side. And the positive side is always the incident ray side. I went positive side. I'll revise it once again, don't worry. And if I want to measure the radius of what you call the purple surface, I will again measure the radius from the optical center. I should have started from here, but this portion is negligible. So I measure R1 on this side. Okay, so this side means I am going negative. Okay, and if I'm going this side, I am going positive. The measurements are always from the what you call the optical center. Now let's see another analogy to it, and you can observe whichever is okay with you. Okay, now a double convex. 1 minute. I have a double convex lens, and the double convex lens can have different radius for either side, right? So this is a double convex lens, and let's say this is C1 and this is C1, and let's say this is C2, C1 and C2, right? Now here we will say that the center of curvature, which is on the emergent side, radius belonging to the center of curvature, radius belonging to center of curvature, which is on emergent side will always, this is the emergent side, will always be taken as positive. Mind the language. Radius belonging to the center of curvature, which is on the emergent side. Forget about the entire spherical part. Just look at the lens. Which side does the ray emerge? The ray will emerge on this side. So C1 falls on the emergent side. So is this getting clear? Radius belonging to the center of curvature, which is on the emergent side, will always be taken as positive. Similarly, radius belonging to center of curvature, which is on incident side, will always be taken as negative. That means this particular radius is positive, and obviously makes a sense because I would be measuring the radius from this side. So for this surface, the radius will be positive. For this surface, the radius will be positive. Sorry. For this surface, the radius will be positive. Just see, are you able to appreciate what I have said right now? Why this surface? Because this surface part is this dotted circle. And the radius for this particular surface will be taken as negative because its center lies on the incident side. Okay. Now, these double convex lenses can be equiconvex lens. Children, can I change this? I'll just change this, what do you call, software. Huh? Just don't mind. Give me a minute. And then we'll revise and then we will go ahead to Prism. Don't worry, because this is important. Otherwise, you will land up in trouble like we landed yesterday. Okay. So let's say this is an equiconvex lens. Understood? This is an equiconvex lens. So in the case of equiconvex lens, in case of equiconvex lens, my R1 will be always equal to R2. No doubt about that, right? And let's see. Now, what is R1? R1 belongs to the surface where the light will actually strike first. R1 belongs to the surface where the light will actually strike first. So let's make our optical center. So this is my optical center. R1 belongs to the surface where light will strike first. So now I'll add colors. I'm adding colors. So R1 I am making purple. So this is R1. Is this clear? This is R1. And you would measure the radius of R1 from where? You would be measuring the radius of R1 from the optical center, and R1 belongs to this particular circle, so its radius will be measured on this side, which is C1, and this would be my R1. So my R1 in this problem will be positive. Pause a minute and let me know you have understood this thoroughly or not. Neha, understood this? Right. Now, once R1 we have obtained, children, there is no problem to obtain R2. So obviously R2 is this portion. And how will you measure the radius of R2? In order to measure the radius of R2, I would be going up till here, which is my C2, and this is my R2, which is actually negative. My R2 will come negative. Fine. Now let us look at our formula. Our formula will be 1 upon f is equal to eta of the lens divided by eta of the medium minus 1, and 1 upon R1 minus 1 upon negative of R2. Clear? And since R1 is equal to R2 is equal to R in an equiconvex lens, my 1 upon f will become equal to eta lens over eta medium minus 1, and this is r plus, so this will become 2 by r. Just see. Understood? So the things that are to be taken away are summary of our discussion. Summary. Okay. R1 light strikes first. Right? R1 belongs to C1 center of curvature, and C1 lies on emergent side, and that's the reason this is always taken as positive. R2 light strikes later, and R2 belongs to a C2 center of curvature, and C2 lies on the incident side, hence taken as negative. Okay? So it says that we have a glass lens. We have a glass lens, and for this glass lens, the f is equal to 0.5 meters. How much, beta? 0.5 meters. The first question is what is the power of the lens? What is the power of the lens? So we say power is always equal to 1 upon f, provided f is in meters, which is 1 upon 0.5, which is equal to 1.0 by 0.5, point gone, so it is 10 by 5, which is equal to 2 diopters. So the focal length in air is given as 20 centimeters, fine, and R1 is given as a value as 10 centimeters, and R2 as a value is given as 15 centimeters, fine, not an issue. And we have to find out the eta of the glass as the lens is made of that medium, fine. So 1 upon f becomes equals to eta of the lens divided by eta of the medium minus 1 multiplied by 1 upon R1 minus 1 upon R2. See, by this time, if anybody would have seen the textbook, the job was done. All reluctant to work hard. So 1 upon 20 becomes equals to how much? Eta lens means the eta of the glass divided by eta of the air minus 1. 1 upon R1 is 10 plus 1 upon minus 15. Sorry, minus 1 upon minus 15. Minus 15. Or 1 upon 20 is equal to eta glass. Eta glass's value will be same as eta glass minus 1. And this value becomes 1 upon 6. So 20 will go that side, or we can straight away cancel them also. So it becomes 6 by 20 is equal to eta glass minus 1. So eta of glass should be equal to 1 plus 6 by 20. So eta glass becomes equals to 1 plus 6 by 20. So 6 divided by 20. And with that, we add 1. So we get 1.3. Perfect. Now, take it down. On the next question, what we have done, we have now put the lens in water, and we now need to find out what is the focal length of the lens in water. This is what we have to find out. So the focal length in air is equal to focal length in not focal length in air. The formula says 1 upon focal length in air is equal to the eta glass minus 1, and here it was how much? 1 by R1 minus 1 by R2. I can write 1 by 6, doesn't make any sense because they will cancel out. Eta glass by eta air, and here it will be,
Sir,
yeah,
yesterday we got eta class is 1.5.
eta glass as 1.5. No, 1.5 is, read the question. The water's refractive index will be given to you. Read the question, third part.
Yeah, it's given as 1.33 for water.
For water, it is how much?
1.33 in the third bit.
Then again, there is some information you are. Eta water is equal to 1.33. Then read the question again for the first part. What is the focal length in air? Read the question.
For the first bit, focal length is 0.5 meters. What is the power?
Focal length is 0.1 meter. 1 meter. For the first part, they said that the focal length is 0.5 meters. And what is the power? So Arjun, you are correct in that. This is the first bit. The second bit. Read the second bit.
The data of question is 10 centimeters and 15 centimeters.
Okay.
The focal length is 12 centimeters.
The focal length is 12 centimeters. That's all. That's all. So the focal length is 12 centimeters. Fine. We'll get it. No worry. So the focal length is 12 centimeters. Oh, so much of time consumed for this silly thing. So this is 12, right? So 6 by 12. Now your answer has come. 6 by 12. 6 by 12 is 0.5. So 1.5. Are we fine now? Okay. Now everything will come correct. Perfect, Zoe, now? Okay. Now we have to find out. Yeah, just tell me perfect. If you raise your hand, I have to be butterfly, like having eyes at the back. So eta H2O is equal to 1.33. We have to find this. So let's find out. So the focal length when you are dipped in H2O will be equal to eta glass. So eta glass remains the same, and eta of the medium now becomes eta of H2O minus 1, and this becomes 1 upon R1 minus 1 upon R2. So if I divide both of them, this and this gets cancelled. So I have 1 by FA, 1 by focal length in air. What is the focal length in air? 12 into focal length in H2O is equal to, now we have eta glass minus 1. What is eta glass? Eta glass, how much did I find out? 1.5 minus 1 straight away. This thing is, air is 1, okay? And this is being divided by eta glass. Eta glass is 1.5. What is eta H2O? 1.3. And this is minus 1. Now it will come correct. Earlier it was coming negative. That was my hunch. So the focal length in water would be equal to 12 times 0.5. And then this will become...
We took 20 in this question.
Which one?
In this subbit. Instead of 12, we took 20.
No, but has they mentioned anything like 20?
Yeah. Focal length in air is 20.
Focal length in air is 20. Okay, fine. So we will make it 20. So we'll make it 20. Okay. The focal length is 20 mentioned out here. So we will make it 20 times 0.5 into 1.3. And this is 1.5 minus 1.3, which is equal to 0.2. So let's do this calculation. 20 multiplied by 0.5, that's half of it, which is 10, multiplied by 13, which is 130, divided by 0.2, which is... No.
Isn't it 1.5 minus 1.3?
1.5. So it should be not 13. This is 1.3. Sorry. So it will be 20 multiplied by 0.5 into 1.3. Still we're getting something less. We're getting around 65. We had to take this as 1 by 12. 1 by 12 is equal to half, 1.5, right? Fine. How much did they get the value of eta glass? 1.5?
Yeah.
Oh, this is 1.33. That's why the approximation is coming. Okay, this is 1.33. Sorry, children. So now this won't be 0.2 then. Okay, this won't be 0.2. Oh, 1.5 minus 1.33. So this is 0.17. 0.17. Okay, so now it will come out 20 multiplied by 0.5 into 1.33 into 0.17. So yes, 78.25. I think this is the answer.
Yeah.
All because lack of that textbook. I need to keep the physics 1 textbook with me, not rely on you guys. Only thing is my textbook is old version, so it has many. We would have got this data very easily. Makes it clear now how to solve problems? Okay. Another, just for your knowledge, if you have a plano-convex, so plano-convex will look like this. This is R1, this is R2. In case of plano-convex, R2 is taken as infinity. R2 is taken as infinity, very, very big radius. Because bigger the radius, more straight it will look. Look, for a smaller radius, it looks curved. For a bigger radius, it is less curved. For an even bigger radius, it is less curved. Now, this is almost a straight line. That means the radius is infinity. Keep that also in mind, okay? Our next topic, we will do problems later on. Our next topic is that of a prism. So, let's have a look at our prism. A prism is equilateral prism. So let's label our prism A, this is B and C. BC is known as the base of the prism. In fact, if you look at a convex lens is a combination of all prisms upside down. See, this is combination of all prisms upside down. So we will have what? We will have our incident ray. So my incident ray comes from here. You're absolutely just attending the class because you all are awake. Okay, this is the normal. Now I'm making the refracted ray parallel to the base due to one reason which we will get to know, but it may not be parallel, but at least it will get deviated. That's for certain, okay? And then I get an emergent ray. So my next normal would be at this surface. So this is my next normal, and I would get my emergent ray. This is my emergent ray. So what we need to name out here, just see, this is my angle of incidence. And then I get my first angle of refraction, which is R1, and I'm naming this as R2, but this is my second angle of incidence. And finally, I get my angle of emergence, which is my final angle of refraction. Could you understand? Because this is, you have an experiment also with this, so you should understand this very nicely. You have an angle of incidence that creates an angle of refraction, and then this is my next angle of incidence, and this is my final refraction, which is known as the emergent. So this is my incident ray, this is my refracted ray, this is my emergent ray, okay? And I now try to trace, if I'm trying to trace the path of the incident ray, and I start tracing the path of the refracted ray, then what do I find? That actually the incident ray had to go in this side, but the incident ray deviated this way. So this angle is known as my angle of deviation. So it's known as my angle of deviation. So I is my angle of incidence, my R1 is angle of refraction, R2 is my angle of incidence. This is my second angle of incidence, this is my first angle of incidence, and E is angle of emergence. and d is delta is angle of deviation. Delta is my angle of deviation. It forms a quadrilateral. Let's call this as AB, and let's call this as C, and let's call this as D. ABCD. You form a quadrilateral which is ABCD. Perfect. Okay. So if you look at the quadrilateral ABCD, if I look at quad ABCD, then opposite angles of a quadrilateral are always supplementary. Okay. Angle A plus angle C is equal to 180 degree. And further I can write angle A plus, instead of angle C, I can write angle C as 180 degree minus R1 minus R2 is equal to 180 degree, which allows me to cancel the 280 degrees, and I write angle A is equal to, so this is R1 plus R2. This is one relation. Angle A is equal to R1 plus R2.
So how did you get 180 minus R1 minus R2?
This triangle, this is angle C. C plus R1 plus R2 should be 180 degree, right?
Yeah.
Okay, fine. Now I'm putting two symbols out here. I'm putting a dot out here and I'm putting an asterisk out here so that I don't mutate the diagram further. Can I write I is equal to dot plus R1, vertically opposite angle, right? And I can also write E as asterisk plus R2. E as asterisk plus R2. Is this possible? E as asterisk plus R2. If I add these two, what do I get? I get I plus E is dot plus asterisk plus R1 plus R2. Perfect. And dot and asterisk will be interior angle for the exterior angle delta. So I plus E is delta plus R1 plus R2. Delta plus R1 plus R2. From here we can get a relation that delta is equal to I plus E minus A. Just try to see whether this is correct or not. Delta is equal to I plus E minus A. A is known as the prism angle. I plus E minus A. R1 plus R2 is A. R1 plus R2 is A. Perfect till here? Right. Have been cancelled. So we come across a relation delta is equal to I plus E minus A. Okay. After this, what we do, we can have a plot. This is what you do in your practicals. You can plot the angle of minimum deviation, sorry, angle of deviation. You plot it with angle of incidence, angle of deviation, and this is angle of incidence, right? So we make a plot between delta and I, and then you will get this plot typically like this. What does this plot signify? It signifies in this manner. Look, if the angle of incidence increases, the delta also increases. And further, if you increase the angle of the incidence, delta starts falling, falling, falling. And then you come at a particular instance where the angle of incidence is minimum. The angle of incidence will, sorry, angle of deviation will be minimum. This is the minimum angle of deviation, right? Now just check this particular expression. Try to see this expression. This expression will give you an equal value for delta. Okay, suppose I make this as 2 and I make this as 3. I get some value. Swap the values. I make this as 3 and I make this as 2. Then also this value will be same. Yes. So this is a symmetry of the equation. Forget about a, whatever is a. This is 2, this is 3. I get a value of delta. Keep the value of a constant and you swap this as 3 and this as 2. Then also delta's value will be same, which actually tells you that there is a symmetry, that the angle of incidence gives you an angle of emergence, and from this side also, if you have angle of incidence, this will become the angle of emergence. And the minimum deviation for that criteria, we say that the minimum deviation happens when the angle of incidence, the angle of incidence equals to the angle of emergence. Angle of, that is the minimum deviation. Try to think, if these two angles are equal, then this deviation would be minimum. Think in a different manner. Try to increase this deviation. To increase this deviation, you have to, there will be deviation. To increase the deviation, what you have to do? This arrow, green line has to come here. The green line comes here means the indigo line also moves up. Okay, I want to have minimum, minimum, minimum. If you want to have minimum deviation, this and this have to be equal. And when this and this becomes equal, then the purple becomes parallel to the base. That's the reason I wrote this. Then the purple becomes parallel to the base. Are we fine? Then the purple becomes parallel to the base. And so at minimum angle of deviation, delta is said to be a value called dm. This is the minimum angle of deviation. The angle of incidence equals to the angle of emergence. The angle of incidence becomes equal to the angle of emergence. Did you understand? And another thing that happens is the BD becomes parallel to, I can't write it as, okay, let me name the prism as AEC. Okay, BD becomes parallel to EC, which means R1 becomes equals to R2. R1 becomes equals to R2, which I am writing that let this be equal to some value R. Children, have you understood this? At a minimum angle of deviation, delta becomes equals to delta dm, and angle of incidence will become equal to angle of emergence. So look at this expression now. So I can write dm is equal to I and E are same, so it becomes 2I, right? And A is the combination of what, beta? R1 plus R2. R1 and R2 both are equal and it becomes R. So A becomes 2R. A becomes R1 is equal to R2. So A becomes 2R, which gives you the value from here as I equal to, let's say the value of I will be equal to dm minus, okay, minus A. Where was our equation? Our A was equal to our array. Okay, our A was equal to R1 plus R2. So from here we can write A is equal to 2R. So we retain this as, I'm retaining this as A. So I will be equal to dm, I will be equal to dm plus A divided by 2. See this? Something wrong we have done. I is equal to E. So this will be I is equal to E at minimum angle of deviation. So it becomes 2I minus A. So just hang on. I think something is wrong here. My angle of deviation dm becomes equals to 2I minus A. So I's value becomes equals to, yeah, dm plus A divided by 2. Okay. What is the angle of refraction? And parallelly, we also say A is equal to how much? 2R. So R is equal to A by 2. So from here, you can find out the refractive index of the prism. Refractive index of the prism with respect to air would be given by sin I by sin R, which is equal to sine of A plus dm by 2 divided by sine of A by 2. So the refractive index of the glass prism is now equal to, you understood this is prism with respect to air. So the refractive index of the prism is given by sine of this is almost equal to this because they are small angles. So it will be A plus dm by 2 divided by A by 2. Something is wrong. So just check the textbook. Are we okay on the prism?
I think we're correct.
Huh?
I think it's correct.
Wrong, right?
It's correct.
It's correct. Okay. No, I was just checking this. It is A plus dm whole thing by 2. Just check that. Sine. Yes. So if you take out the sine of the angles are so small that the signs can be neglected. So A plus dm by 2 by A, which means that the angle of deviation for prisms are very minimum. This will be equal to A by A, which is 1. 1 plus this. That means 1 means, are you trying to understand what is the value you're getting? Dm divided by A will be a very small quantity. And this is coming almost equal to 1. Almost equal to 1 means this refractive index is almost like a air. Air's refractive index is 1, right? So this is almost like air. So the angle of the refractive index is very minimum. So the prism will deviate very less. Just a quick look how we got this. So we say that first of all, you establish the relationship in the quadrilateral A plus C. A plus C will give you value of 180 degree. Instead of C, you take out R1 plus R2. So A becomes equals to R1 plus R2. And at minimum angle of deviation, this will equal to this. So here it becomes I plus I. So it becomes 2I minus A. So I becomes dm plus A. And R becomes A by 2. Just do the sign of both and you get it. We are now just left with microscope and telescope. Today it was a slow class. I mean, that problem took a lot of time. So maybe on Tuesday we will be able to wrap up microscope. 2 to 3 more classes on this chapter. Okay, could you note it down? And at minimum angle of deviation, the angle of incidence will always be equal to the angle of emergence. At that time, this line becomes, this refracted ray becomes parallel. And there are two values of I and E. So if you swap the values of I and E, the value of delta does not change, which means that you can use this side also as incidence. You can use this side also as incidence. Both are valid. Are we okay? Then we'll conclude.